Well, thank you very much for the introduction. And at this point, I would also like to thank the organizers for the fantastic school the last 2 weeks and for the coming week in advance. So as Chair already announced this morning, I have been working on an experiment where we want to collapse quantum mechanics just to figure out whether there's some intrinsic boundary to the theory. But just to take a few steps back at first, let's consider the main idea of the experiment. And, well, today is a very important day, actually. It's the 5th of December, in which, in the Netherlands, we celebrate Sinterklaas. That's Sinterklaas. And for the moment, you can just think of him as the American version or the Dutch version of the American Santa Claus, but in fact, it's all the other way around. But whenever children ask to grown-ups, well, how can it be that Sinterklaas is at all places at the same time? We would answer them, well, that is because there's a lot of hulp Sinterklaasen, people that help Sinterklaas, who are doing his job for him. But here I want to propose another theory, namely that Sinterklaas figured out the principles of quantum mechanics already quite some time ago and actually creates a superposition of himself. So here he is dividing the presents, and here he is listening to children's wishes. Well, this sounds like a ridiculous story, but quantum mechanics doesn't tell us why it is a ridiculous story. I mean, there's some interpretations of quantum mechanics around where the Copenhagen interpretation just tells us, don't ask the questions and you will be fine. There is many worlds. That's, well, it's not a falsifiable theory, so why not? Well, we can't probe into different universes, right? Yeah. Let's keep questions to the end. This is not the main point of the talk anyway. And there is environmental decoherence, what Chair argued this morning, can't really explain the collapse after all. On the other hand, there's the theories of GRW and CSL that say particles that have too large a mass collapse spontaneously, or there's theories around that say, okay, we have an ill-defined space-time, and that mainly boils down into an uncertainty in energy and time. So let's get back to Sinterklaas, because how would he do it in the end? Well, Sinterklaas, there he is, would need to make himself really small. Then he would go through a beam splitter and create a superposition of himself, but, well, we can't really see small things, so he would, again, amplify himself with an amplification G, and he becomes a little larger. Then, if quantum mechanics works out, he applies his phase shift, and we would observe some kind of interference pattern. Now, what would happen if Sinterklaas fails and tries to create a version of himself that is too large for quantum mechanics, whatever that means? Well, he would again create a superposition, but this time apply too large an amplification, creates a big picture of himself, but, well, he collapses, and the interference pattern is lost. To make that a bit more quantitative, let's consider the same setup, but this time not with Sinterklaas, but with a single gigahertz photon source. Well, what we need to do to see what comes out at the other end is we just do Schrödinger evolution from the beginning of the setup all the way till the end by the Hamiltonian. So as a first, we have the beam splitter, or which is called in the microwave domain a hybrid, and that applies a phase shift between channels 2 and 3, or the upper and lower channel, of a half pi. And the transformation matrix is given by this unitary. Well, if you just compare the unitary matrix and the Hamiltonian, then you can see that the Hamiltonian would be just the same, only without the exponential factor. The same you can do for the phase shifter, which now is not behind the amplifier but in front of it, and then you would end up with another corresponding Hamiltonian. And for the tupa, the Hamiltonian basically says that the two pump photons are transferred into one signal photon and one idler photon. And why is the pump not there? That's because we assume that the pump is undepleted and it goes into this prefactor kappa. And as for the gain, you can determine the gain, the decibel gain, as the cosine hyperbolicus of this factor kappa. Well, then we just use the numerics of QTIP, which is a quantum optics package for Python, and we see what comes out. Well, let's first make sure that everything is implemented right and do some verification, where I want to point your attention to output channels 6 and 7. And if we input the single photon on channel 1, then we expect it in channel 7 and not to appear in channel 6. So if we then apply a phase shift at a kappa of 0.4, then we see a nice interference pattern coming out, and also for the idler, where in fact the idler is to be expected more in channel 6 than in channel 7. And on the other hand, if we set the phase shift to 0, then we can also see what comes out for the mean number of photons on each of the two output channels for both signal and idler, and we see that indeed it works like an amplifier. Well, this is just a mean, but you can also do statistics on averages, where here in red is just the standard deviation. So this is the mean, this line corresponds to the mean plus standard deviation. Here in red is mean minus standard deviation. So the number of photons becomes, so to say, not really well defined anymore. Okay, but we want to see interference in the end. And we do that generally at using some visibility. Well, if we keep the phase shifter at a phase shift of 0, then you would find that the visibility is just given by the difference in channel 7 and channel 6. So that's the two output channels. And you can define it in two ways, which each correspond to either measuring this experiment with a spectrum analyzer, in which you have a long integration time, so you would take the averages everywhere, but you could also measure it using a lock-in, in which you can see actually the single photon Fock states arriving. And in that case, you can do some more statistics, which is in the distributed version of the visibility. So, what comes out? This picture I made for both the average and the distributed version of the visibility. So to walk you through it, because it's quite information dense. So for the average version of the signal, we find that it starts at 1 for the signal photon, there's no amplification, and then it gradually decreases to a visibility of 1/3. For the idler, the average visibility is always 1/3. And for the signal which is distributed, it keeps a little higher, but and there is also some uncertainty involved. It gradually decreases to 1/3, and for the idler distributed, it gradually increases to 1/3. So the 1/3 is the value that we will end up with. As you might notice, I went up to a kappa, so a nonlinearity parameter of 1.5, after which my computer said, no, not gonna do it, I just crash. Right. So the whole endeavor was started to see this collapse. So what would be the hint that we really see collapse? Well, just quite intuitively, we would assume that a collapse is triggered as a Fock state or a superposition of Fock states collapses into a coherent state, because the coherent state is classical state. So before the collapse happens, so this is the Wigner function that I calculate for a nonlinearity parameter of 0.4 at position number 5, which also incidentally is the same as position number 8 in the IQ plane, which is just the in-phase and out-of-phase quadrature of the experiment. And what you see, it's nicely round, so the phase of the photons coming out is not really determined. Oh, already there. I'll speed up. And in the middle, there's a dip, and this is really, therefore, really quantum. But if it collapses, then it might happen that there are coherent states for the signal in 5 and the signal in 8, which are just chosen randomly like this. On the other hand, there's the same probability that not this collapse happens, but precisely the other way around. And that is because the photon can either has a probability of 50% to go through this arm and 50% to go through this arm. But this corresponds to a certain splitting in output photons, and this would correspond to exactly the opposite splitting. And therefore, if you would average over everything, there would be a visibility of 0. What about losses, however? Because the losses will also tend to get the visibility down. And, well, from this Hamiltonian, we can apply the Lindblad formalism through the whole setup, and we introduce some jump parameters that just correspond to a photon jumping out of the system to the environment, or vice versa. Then we can vary the time that the photon or the state spends in the tuba to vary the loss, because in the end it's the factor gamma delta t, where gamma is the dissipation rate, that is relevant. And, well, gamma delta t, you can think of it as the amount of photons that have left the system. And for the other components, I just assume that gamma delta t is 0.1 for the moment. In that case, well, indeed, we see that the visibility goes down for the signal, and it goes, if you vary the nonlinearity, slightly up for the idler, and that, well, it goes down for the signal because there's already initial signal, and it goes slightly up for the idler because there is initially no idler left. But anyways, even if you lose 2 photons, there is some visibility left. And what we would see that when the collapse is triggered, that it goes faster than what is predicted here. So what we would measure initially is the loss of the 2 parts. Well, then there are some difficulties because I've assumed throughout this talk that the two amplifiers are the same. But what if they aren't? And on the other hand, a cryogenic phase shifter is not a trivial thing. With that in mind, I have some acknowledgements to make. First, Luc Rademacher, who is formerly Leiden University, but now moved to UCSB, helping me on the calculations and the interpretation of the calculations. Also, Michiel de Dood, who's still at Leiden. And of course, I'd like to thank my whole group and Nanofront for subsidizing my project. And with that, I'd like to thank you for your attention, and I presume there are no time for questions anymore.
Yes, thank you very much for your nice talk.